Hello again, physics friends. Today we're going to talk about position, velocity, and acceleration expressed in 2D polar coordinates. And in order to write those out properly, we need to address how to take the time derivative of the r hat and phi hat unit vectors. So that's where we're going today. Recall we can identify the trajectory of an object as a function of time and talk about the position vector to that object. And we have said before that we can write down the position vector, let's say r1, which in this case is the position at some time t1, and we can write that in terms of a distance from the origin and a unit vector. So we can draw here the unit vectors. We have the r1 hat unit vector. And what do I mean by r1 hat? By that I just mean the r hat vector at time t1. And what we have already pointed out is that sometime later now, the object is in a new location, and at that new location there's a new position vector, which is the position vector at some later time t2, and there's a different unit vector now where r2 hat is the direction at the radial direction at time t2, not t1. We've also pointed out that there's a second unit vector because we're talking about two-dimensional coordinates, and we call that phi hat. And phi hat and r hat are perpendicular to each other. We can write it as phi hat 1, which is the phi hat unit vector at t1, and then phi hat 2, the phi hat unit vector at time t2. And notice that those two are orthogonal to each other. The r hat vector and the phi hat vector are perpendicular to each other, and that's true for all time, even though the pair of those vectors might rotate in time. So how does this all relate to time derivatives of unit vectors? Well, recall that we had position in 2D polar coordinates we could write as a distance from the origin multiplied by a direction. And we then said the velocity could be written as the time derivative of the position vector, which is the time derivative of a product of two quantities, a scalar and a vector. So we have dr dt, the r scalar, in the r hat direction, but by the product rule we also have r times the time derivative of the unit vector, and so on. Okay. And what we claim is that this is going to shake out, at the end of the day, it has to be something times the r hat direction plus something else times the phi hat direction. In other words, your velocity vector can have a radial component and it can have a tangential component. Okay. And what we're going to show is that the radial component is r dot and the tangential component is r phi dot, or r omega. So we have a radial component, v radial, and we have a tangential component, v phi. The acceleration is going to be the velocity's time derivative, or the second derivative of position. And we're going to get now another product rule, and in this case we're going to get a triple product rule. We'll get three terms out of that time derivative. And so what we'd like to show is that the acceleration is given by the following: r double dot minus r phi dot squared in the r hat direction plus r phi double dot plus 2 r dot phi dot in the phi hat direction. the first term in parentheses is the radial acceleration, whereas the second term is the tangential acceleration. So we're going to go through this derivation, and along the way, we're going to have to prove something about the time derivatives of the r hat vector and show that it's proportional to phi hat. And then we'll have to compute the time derivative of the phi hat vector and show that it is proportional to r hat, but with a minus sign. So that's where we're heading. Okay, so I'm going to make some space here. I moved our position, velocity, acceleration up there. And now I'm going to start with goal number 1, which is to show that the time derivative of r hat is parallel to the phi hat direction. In other words, the direction in which r hat is changing is the phi hat direction. And that's going to come into play when we get rid of dr dt, or rather replace dr hat dt with the phi hat term. So let's see why that's true. Well, you've already actually proven that this is true, right? We said, we've shown that if we have a vector A with constant magnitude, we showed that the time derivative of A is perpendicular to A. In other words, A dot dotted into A is 0. How is that relevant here? Well, instead of the A vector, let's use the r hat vector. Is the r hat vector a vector of constant magnitude? Yes, it has a magnitude of 1 always. And so what this proof tells us is that the time derivative of r hat must be perpendicular to r hat. And if we look back at our picture, it's certainly the case that the phi hat direction is perpendicular to r hat. Now, are there other directions that are perpendicular to r hat? Sure, it could be the opposite direction from phi hat, it could be out of the page, and so on. We know that we can ignore any directions that are out of the page, though, because the r hat vector, although it evolves, it never evolves to have a component out of the page. So if we restrict ourselves to considering perpendicular vectors that are in the page, in the plane of the page, then the answer is either going to be the phi hat direction or the minus phi hat direction. So how can we choose? How can we figure out if the time derivative of r hat points parallel to phi hat versus anti-parallel to phi hat? Well, to figure that out, let's take a look at these r1 hat and r2 hat vectors. So I've copied them over here, okay? And I've just moved them so that they have the same point of origin, but I've done my best to recreate the vectors as they were. I made them a little longer for clarity. So if we think about what do we mean by a change of the r hat vector, what I mean by that is in order to create the r2 hat vector, I have to start with my r1 hat vector and add a change of r hat to that. In other words, to get this r2 vector, I have to first have r1, and then I need to add a second vector to that. So I can draw my second vector like this, delta r hat, that's this term here. Okay. So that helps me select the direction of r dot, the rate of change of r hat. So I can see that it's up and to the left and not down and to the right. And so that selects the phi hat direction over the minus phi hat direction. So this helps us understand that dr hat dt, also known as r hat dot, is parallel to the phi hat direction. Okay, with that goal in the bag, let's move on to the next goal, to show not only that the rate of change of r hat is parallel to phi hat, but specifically what is that proportionality constant. And what we're going to see is the time derivative of r hat is equal to phi dot in the phi hat direction. So let's make that work. First, we'll reshuffle some of the stuff that's over here so we can give ourselves a little more space. Okay, so I have my triangle here formed by the two r hat unit vectors and the delta r vector. And I'm just going to label in here an angle, which is delta phi. That's the difference in the phi angles between time 1 and time 2. Now this kind of looks reminiscent of the arc on a circle subtended by some angle, right? So if I draw a circle and I identify my two radii and I call out an arc length S subtended by an angle theta and a circle of radius r, we can relate the length of this arc to the radius of the circle and the subtended angle, S equals r theta. So we're going to see that there's something similar that we could apply to this triangle here. And that would be that the length of the green vector, delta r hat, is equal to the radius of the circle. If we imagine this to be a circle with these radii, which are unit length because they're unit vectors, and you can pick either one, times the angle subtended, which is the delta phi. Well, like I said, on the right-hand side, this term magnitude of r1 hat is just 1. It's a unit vector, so it has length 1. So on the right-hand side, we are just left with delta phi, and on the left-hand side, mag r hat, the magnitude of r hat. Okay. So let's think now about the quantity that we're trying to solve for. We want to know what is the magnitude of the rate of change of r hat. Okay. Well, that is a derivative. That's the limit in the limit of small time intervals of delta r hat delta t. But we know something about this length of delta r hat. We just said it was equal to 1 times delta phi. So our limit could be written instead as delta phi by delta t, but that whole limit is, in fact, the derivative of phi with respect to t, which in our dot notation is simply phi dot. Okay, so in the first case, we've shown that the time derivative of the r hat vector is parallel to phi hat, and in the second analysis, we've shown that the magnitude of the r hat rate of change is equal to phi dot. So if we put those two together, then we see that the direction is given as phi hat and the magnitude is phi dot. So that tells me that the vector itself, dr hat dt, has to equal phi dot in the phi hat direction. And we are done. That's what we tried to show. That's what we wanted to show. Okay. I'm going to show the same thing another way, but before I dive into that, let's just take a moment to look back up here, okay? We have r dot in the r hat direction. Those are these first two terms. And now we have r times the time derivative of r hat, which we now know is phi dot phi hat. So I have r phi dot phi hat, r phi dot in the phi hat direction. So we've derived now the velocity vector in 2D polar coordinates. And we see that although the position vector has only a radial component, there's no such thing as the tangential component to position. You just walk from the origin radially outward to where you want to go. The velocity can have both a radial and a tangential component. Okay, so now I'd like to transition to getting at this same result a very different way using linear algebra and rotation matrices. This is an optional a thing. If you prefer to skip it, that's fine. You can jump ahead a few minutes. Okay, so let's start by thinking of taking a very specific example. Call it example 1. Let's consider the case where r hat is parallel to the x hat direction. Okay, so that might happen at one instant of time. It might be the case that you have a particle sitting on the x-axis. Okay. And so the position vector, the r vector, I should use different colors, I think. Excuse me. How about purple? Purple for position. The r vector points to the right, and that means our r hat vector, the unit vector, in the radial direction, points to the right also. And we know the phi hat vector is going to be a 90-degree counterclockwise rotation from r hat. Okay. So at this instant of time, we have the r hat vector has Cartesian coordinates 1, 0. It points strictly in the x direction, and it has a length of 1. And the phi hat vector is 0, 1. It has a length of 1, and it points purely in the y direction. So we can also see that phi hat is equal to r hat rotated by 90 degrees, pi over 2 radians. Okay, and this statement, rotated by some angle, can be represented in linear algebra as multiplied by a rotation matrix. Okay, so let's see how that plays out. Rotation matrices, I might label it r theta, where theta is the rotation angle. We can write that as cosines and sines in a 2x2 matrix. The diagonal terms are cosines and the off diagonals are sines. And notice that one of the off diagonal terms has a minus sign. Okay, so let's check that that's really true. Okay, so let's check. The claim then is if I'm rotating by pi over 2, I would have a matrix that's cosine pi over 2 minus sine pi over 2, sine pi over 2, and cosine of pi over 2, which is the matrix 0, minus 1, 1, and 0. Okay, so let's see if that's true. If I have the the x hat unit vector, which is 1, 0, and I multiply that by a 90-degree rotation, I would expect to get the y hat unit vector, just like we did up above. Is that really true? So let's see. Our rotation matrix claims to be 0, minus 1, 1, 0, and our x hat unit vector is a column vector 1, 0. And when I multiply that out, I'm going to get another 2x1 column vector. So when I do my multiplication, I get for this first entry 0 times 1 plus minus 1 times 0. So that indeed gives me 0. And then in the bottom entry, I'm going to get 1 times 1 plus 0 times 0. That's 1. And indeed, that is the y hat unit vector. So what I've shown is if I multiply by this rotation matrix, I've rotated x hat into y hat by multiplying by a 90-degree rotation matrix. Okay, so that's good. So this phrase that I've written up here, phi hat equals r hat rotated by 90 degrees, now I can give it a more mathematical flavor. I can say phi hat must be equal to a rotation matrix by 90 degrees times the r hat vector. Okay, good. So if I only knew how to write the r hat vector in Cartesian coordinates, I could then use this rotation matrix to figure out the phi hat vector. So let's see how we can write the r hat vector in Cartesian coordinates. Okay, so I've drawn a set of axes and I've drawn my r hat vector pointing in some arbitrary direction, not necessarily aligned in the x hat direction. Okay, and I'm going to try to break this into components in the x and y directions. And what do I know? I know that in polar coordinates, I also have this angle phi, which is that angle phi. So I should be able to break down the r hat vector into its components, okay? So that might look like the vertical component would be, would have a component which is magnitude of r, the length of the hypotenuse, times the sine of phi. But since the magnitude of r is just 1, the vertical component would then be sine of phi. You can do the same thing for the horizontal component, the x component. It'll be mag r times cosine of phi. Magnitude of r is, once again, unity. So the horizontal component is just cosine of phi. So that means I can write out the unit vector, the r hat unit vector, in Cartesian coordinates as cosine phi, sine phi. So that's cosine phi in the x hat direction plus sine of phi in the y hat direction. So the claim then is that my phi hat unit vector will be equal to a 90-degree rotation of my r hat unit vector, but I now have specific values I can put in for my rotation matrix, 90 degrees. That's 0, -1, 1, 0. And now I also have specific values I can put in for my r hat vector. It's cos phi, sine phi. Okay, so when I multiply this out, I'm going to get yet another vector. And it will be a 2-element vector, x and y. And my first element will be 0 times cosine plus -1 times sine. So that's negative sine. And my second component here will be 1 times cosine plus 0 times sine. Okay, so now I have an explicit statement about the phi hat vector. In particular, the phi hat vector would be minus sine of phi in the x hat direction and positive cosine of phi in the y hat direction. Okay. And if we come over to our diagram over here, we're going this length in the negative x direction. And then we're going to go the length cosine phi in the y direction. And when you put that all together, that gives you the phi hat unit vector. So we want to verify that those two vectors are perpendicular to each other, number one. And we also want to verify that if I take my r hat vector and I take its time derivative, I better get back a vector that's parallel to this phi hat direction. So let's do that and make sure that it's true. Okay, I've made a little space for ourselves here. And just a reminder, our goal is to show the time derivative of r hat is equal to phi dot phi hat. And what are we given? What are our starting points? Well, we know how to express r hat in Cartesian coordinates, and we just figured out how to express phi hat in Cartesian coordinates as well. So let's just get started. We'll do the time derivative of r hat, which is the time derivative of this Cartesian expression of r hat, cosine phi in the x direction, sine of phi in the y direction. And when I take that derivative, I have to chain rule. I'm going to do derivative of cosine is minus sine. And then that gets multiplied by the derivative of the argument of that sine function. For the y component, derivative of sine is cosine. And I chain rule through to get a time derivative of phi. Okay, So notice here I have a phi dot in both terms, so I can factor that out. And inside, I'm left with minus sine of phi, comma, cosine of phi. But notice that is exactly the phi hat unit vector. So what we've shown is that the rate of change of the r hat vector points in the phi hat direction, and it has a magnitude of phi dot. So in words, what does that mean? It's saying the faster that you are moving, the faster that your polar angle is changing, phi dot, the more rapidly the r hat vector is changing. And that actually is sensible, right? If you are somewhere in this plane at time 1, and your position vector points right there, and if you only move radially outward, so that at time 2 you're out here, your angle phi hasn't changed at all. So your r hat vector also hasn't changed. So, oops, we'll use red. So at t equals 1, r hat points that way. At t equals 2, r hat points in the same direction. So in this case, phi dot is 0. We're just moving radially outwards. And so is r hat is a constant. So dr hat dt is also 0. So that makes sense. But consider the other case where you're rapidly moving in angle. So at t1 you're over here, and then at t2 you're over here. Well, that's a very major change in the direction of r1. R1 hat becomes now pointing over up and to the left, say. So that's a big change in the r hat vector. And that corresponds to a very rapid change of phi. Okay, so that wraps up our little interlude for another method of showing what dr hat dt is in terms of phi dot and phi hat. So now we're going to come back to position, velocity, and acceleration in polar coordinates. Okay, so just to make sure we're all on the same page, we're starting with the statement that r vector is equal to r hat, and we want to know v. Well, that means we have to take a time derivative of the position vector, which is r dot in the r hat direction plus r times the time derivative of r hat. In other words, we've done the product rule on the two terms of the right-hand side of the position vector, and we know, what do we know? That the time derivative of r hat is phi dot phi hat. So we can make use of that. In the following way. Okay. And as we've said before, we can think of these two terms as the radial component of the velocity and the tangential component of the velocity. So the radial component of the velocity is r dot. The tangential component of the velocity is r times the angular speed, phi dot. Okay. So let's take a look at this graphically. I'll draw my axes. I'll draw a velocity vector that points at some location. Sorry, so we're going to say, let's say we're sitting here. Okay, and I'm going to connect that point to my origin. And that defines the radial direction. And a rotation of that direction by 90 degrees defines my phi hat direction. And let's say I have a velocity vector at this location that is something like this. Okay, my velocity vector has a component in the radial and a component in the tangential directions. Okay, so this component would be v sub r, the radial piece, which is r dot. And this component here would be v sub phi, which is r phi dot. So that's what we mean by the tangential and the radial components of the total velocity. Okay, great. So now we're ready to march ahead and look at the acceleration, which is the rate of change of the velocity, or if you'd like, the second derivative of the position. All right. So I'm going to work out the algebra down below. The time derivative of the velocity is the time derivative of all of this stuff. R dot r hat plus r phi dot phi hat. Okay, so the first term is going to give us two terms by the product rule. We'll get r double dot in the r hat direction plus r dot times the derivative of the unit vector. And then this trio of terms is going to break out into three terms by the product rule. We'll have an r dot phi hat. So that's where we took the derivative of the first term, left the other two alone. Then we'll take the derivative of the second term, leave the other two alone, plus r phi double dot phi hat. And now we'll take the derivative of the last entry, leaving the first two alone. Okay. And here we can pause because we have something we've never seen before. Right? Everything else we've seen, r hat, dr hat, dt, phi hat, but now we have this d phi hat dt. Okay, so we need a little mathematical aside here to figure out what is d phi hat dt. Well, recall from earlier in the video that we wrote out the unit vectors r hat and phi hat in Cartesian coordinates. So let's just use that in order to figure out what d phi hat is dt. Okay, so ddt of phi hat is the time derivative of minus sine phi cosine phi, which is equal to minus phi dot cosine phi, comma, minus phi dot sine of phi. We have a phi dot in both terms and a minus sign, so we factor those two out. And we're left with cosine phi, sine of phi in our vector. But that is exactly the r hat direction. So look at that. How beautiful. How beautiful. We have an expression for the time derivative of the phi hat vector, and it is anti-parallel to the r hat direction. So now we're basically just in need of some algebra. Okay, we're going to try to group terms here, and we'll do it in the following way. We'll recognize that this final term, r phi dot times the time derivative of phi hat, can be written as minus r phi dot squared r hat. Right, so we're making use of this identity, plugging it in here, and we end up with that. So in purple, I'm going to highlight all of the terms that involve r hat. There's two of them. And then we have three terms that involve phi hat. How do we know that? Well, we also want to make use of the time derivative of r hat. So we can re-express this as this term here as r dot phi dot. In the phi hat direction. So that means these three terms are all phi hat terms. And notice that this first green term and the second green term are exactly equal to each other, so we get 2 times that term. Okay, so we have 2 terms in the r hat direction and another 2 terms in the phi hat direction. The 2 terms here are the purple terms. And the phi hat terms are r phi double dot plus 2 r dot phi dot. And that's your acceleration. Now, we can think of the coefficient of r hat here as the radial component of acceleration, and the coefficient of the phi hat we can think of as the angular or tangential acceleration. Good. So now I'm just going to copy this up above so that we have everything all in one place. Whew, okay. We now have a complete expression for position, velocity, and acceleration. Okay. Notice that the acceleration is not so trivial, right? There's 4 different terms and it involves 2 directions. So we're going to have to digest what all those mean. And what I'd like to do later is talk through very specific cases, special cases of this general case. So we'll get to that in the next video, but for now we're going to wrap up having derived position, velocity, and acceleration in 2D polar, and in a subsequent video we will interpret and think through how to use these expressions. Until next time then, take care and be well.